So we've been talking a little bit about heat transfer so far. Now we need to get into a little bit more detail there with the mechanisms for heat transfer. So far we've really only looked at one of those, the one where molecules are bouncing off each other and transferring energy. And that goes along with what we'll call radiation. With what we'll call conduction, not radiation. The other two, though, are radiation and convection. Those are the primary methods of heat transfer. So let's look at these individually. First off, conduction we're more familiar with. This is when molecules that are moving faster or they have more thermal energy or more heat energy. They collide with slower molecules, and there's a net transfer of energy from the faster one to the slower one. So one question we can look at with this is a question I get asked usually once a semester or twice a semester. What would happen if you took off your spacesuit or if you took off your helmet while you were in space? Would you freeze right away? Because people hear that the temperature in space is extremely, extremely cold, like 4 or 5 Kelvin, or maybe even, I think it's a little less than that even, like 2 or 3 Kelvin. So if you did that, would you just freeze instantly? And so this image is from a movie called Mission to Mars from a few years back, and in that movie he took off his helmet while he was in space, and we saw him just instantly freeze. So is that realistic? Well, sadly, or happily, depending on your point of view, no, that is not realistic at all. Yeah, it's very, very cold in space, but remember, what matters for how you feel and how your body behaves is not the temperature in the space, it's the temperature of your skin and of your organs and your body that matters here. So we care not about how warm or cold space is, but how able that space is to transmit energy, to transmit heat away from our body. So we have our warm body here with fast-moving atoms, and that energy will get transferred to cooler atoms, cooler molecules, slower-moving molecules whenever they collide. But that's the problem. This guy is in space. You can see Mars behind him, but he's in space. And space is very nearly a vacuum. That means that there isn't stuff in space. There aren't those particles, or at least they're few and far between. So the collisions, they just don't happen that often. There aren't that many molecules to collide with to transfer the energy to. So, no, we wouldn't just turn into an astronaut sickle right away. It would take an extremely long amount of time for the heat to be transferred away from our body by conduction. In fact, it would be, just a really, really long period of time. We use thermoses here on Earth to try and keep our coffee hot or keep our iced tea cold, and the way that some of these thermoses work is there is some cup and then this layer outside of the cup, and we try and get this area right here to be a vacuum. We take out as much of the air as we can there, because when that's a vacuum, there's no place for the heat inside this cup to go in this area, or at least it's much slower if that happens. And we still have conduction with the air around on the outside, of course, and through the material itself we have some conduction, but there's not going to be that same level of conduction as we would have in just a coffee mug. Our next type of heat transfer is convection, and convection depends on a couple things we've talked about already: thermal expansion to begin with, and buoyancy. So a lava lamp is an excellent example of convection in action. In a lava lamp, we've got a little light bulb down at the bottom of the lava lamp here, and that light bulb is heating up this fluid. The fluid there is a mixture of water is the clear stuff, and the colored stuff it's kind of a waxy stuff. And so when the wax gets warmed up, when it's near the light bulb, it expands. And the water, there's some change in size of the water too, but the wax, because of the properties of the wax, it expands more. And it expands so much, in fact, that its density, whenever something expands, it has the same mass, but now a larger volume, so its density is going to decrease, and it's going to become less dense than the water surrounding it. So that lava, that wax stuff, it's going to float up toward the top, because it's less dense than the water around it. There's a net force upward caused by the interaction between the buoyancy force upward and the weight force downward. So the lava stuff, it floats up to the top, but up at the top there's no light bulb. So up there, that heat that it's taken in, it can conduct through the glass here and through the little bottle cap up at the top. It loses that heat, it transfers outside the lava lamp. So that wax cools off, it contracts again, it becomes more dense even, in fact, than the water around it, and it starts to sink back down. So we get this little process where our lava goes up, and then where it sinks back down. And then this just keeps repeating. These little arrows we can sometimes call convection currents. So the water and the lava, they kind of follow this little circular path again and again. You can see the same thing when you boil water on the stove. You can see the little bubbles, or if you put some rice in there or something, you can see the rice following these little circles, moving up near the center and then falling near the outsides away from the heat source. And then the last way that heat gets transferred, or the last of the big ones, is radiation. And so radiation is a little bit more complex idea. We have to understand something about the structure of the atom, the idea that we have the nucleus of the atom in the middle, and then the electrons on the outside, and the electrons are all at these different energy levels, and this is that simplified Bohr model. And so we can have an electron here jump to a higher energy state if it has enough energy to do that. So it would have had to get energy somehow. And then when it's up at this higher energy state, it can jump back down to a lower energy state. But the energy that it loses when it goes to this lower energy state, it can't just disappear. What happens is a little photon of light, a little quantum of light, or a particle of light, is emitted from this, and so that's a photon. And that energy travels as light, and the color of that light or the frequency of that light is going to depend on how big of a jump there was between these two spots. And then that photon, it can go to some other atom or some other molecule. It can hit that, cause one of its electrons to jump up to a higher energy level, or cause it to vibrate more, and so have more energy that way, have more heat. So one place that you would see this, if you're in an area where it snows, like we are here in Iowa, and we're seeing a lot of this right now, it's February as I'm recording this, is after a snow, when we get to a sunny day, we see that the snow around trees or other dark-colored objects in general will be the first to melt, and then that melting spreads outward from there. So we get melting first around here, and then it gradually spreads out. Now, why would that be? All the stuff here is at about the same temperature. I mean, the trees have been outside all winter, so they're not like super warm or anything. They're they're just as cold as the air around them for the most part. Well, they are until we get to that sunny day. On the sunny day, we have light coming in and hitting these trees. And when that light comes in, the trees absorb that energy. And as a result, two things happen. First, the tree gets a little bit warmer, so that can contribute to some of the melting. But the other thing that happens is these trees will actually emit their own light, but instead of being focused in the visible part of the light, it happens to be more along the lines of infrared light. Now the snow is really good at reflecting visible light, and that's why it looks white to us. White things are things that reflect all the different colors of visible light well, but it's not very good at reflecting infrared light. In fact, it tends to absorb a lot of infrared light. And so this infrared light that's coming off the tree, it absorbs this visible light and this ultraviolet light and emits this infrared light. That infrared light then gets absorbed by the snow, causing the snow to warm up a little bit, or causing it to have a phase change, causing it to evaporate. And so our snow disappears, not really disappears, but it's no longer snow, from the center of this, or from where the tree is, and then expands outward from there.